efficient means it talks about how well does the equation correlate to the data. Does it actually follow what the data suggests? If the value is close to 1, as we talked about here, it means that the equation does a very good job of explaining or forecasting the behavior of the data. If the value is close to 0, not so much. It could actually mean that what you really have there in that equation is just some garbage and not to be used to try and describe that data. The graphs that I've provided in these initial slides are all from an Excel spreadsheet. In Excel, it's fairly straightforward to get the data. If you right-click on one of the data points, you can then ask for a trend line, and that trend line can be any of a variety of different models. And then you can also select to have the R-squared value reported. When you do these things from the drop-down menu, you will then be given the equation as well as the value for R-squared. Okay, so those things come pretty easily. You will have then a couple of different values. This typically is going to be the initial value, or how many you had at the start. Then you have here your growth factor. 4.402 is the growth factor. And it's entirely possible that instead of being given an equation like this, if you work it in Excel, the equation may actually have e to some power, as we discussed over here and talked about a technique for converting from e to a growth factor like this. Either is a fine way to represent the regression equation. We talked about domains. We talked about computing how many there are at the start. Okay. We talked about things like the R-squared value. What does it mean? We also talked about if you have an equation, you can use that equation to forecast a future situation, a future scenario. So for example, with the Ebola, if the disease went unchecked for a year's time, the suggested number of infected people by a year would be 73 million. This brings us to a second example. The second example is also going to be an increasing exponential model. And with this, what we are given is a number of days and the number of bacteria in this system per day. This is not a relatively fast rate of growth for bacteria. It's actually fairly slow, but it's the data that we have. If you do a scatter plot, in other words, just put the points, okay, there are a couple different models that might seem reasonable to fit. One of those being something of a graph, after working with the window, you look for the location where the two functions intersect. Come on down, and that'll give you then the x value or the number of days. A second and more accurate way to determine how many days it will take for the bacterial count to reach 10,000 is to solve things algebraically. By solving things algebraically means that we're going to take the 10,000 and set it equal to the 599.06. First thing you want to do here is to divide both sides by the 599.06. And when you do that, you're going to get 16.693 equals, so what we wound up with here in the intermediate is 16.693 equals 1.188x. We're going to apply the natural log to each side, as we did earlier with exponential functions, but it's not going to play quite the same. What's going to happen here when you apply the natural log to both sides is it's going to allow the x to come out front, the exponent will come out front and become a coefficient. But we're going to have a natural log of 1.188. It's not going to be a scenario where the natural log and the e cancel. These will not cancel this time. And what you get is this equation here on the third line where you have x times this, which is actually a number. Dividing both sides by this natural log gives you whatever was on the left side divided by whatever was on the right side. Now, to compute the fractions value, one way to do this would be to first compute what is the natural log of 16.639 and jot down the 2.815 value. Then compute the natural log of 1.188 and jot down the 0.172. Take the 2.815 divided by the 0.172, and this will give you a final value of 16.366 days. I would encourage you to step through this process, work it out on paper, because you are going to need to be able to do this on quizzes, tests, and the final exam. Be sure that you can do this both by hand and the parts that require the calculator, be able to do it on the calculator. At this point, we need to consider our solution. Is it acceptable to leave it as a decimal, or do we need to convert it to an integer? Well, in this case, it's days. Is it acceptable to have a third of a day? Well, sure. A third of a day is about 8 hours. So 16.366 days is about 16 and a third days, which tells us that in about 16 days and 8 hours from the start of the experiment, you would wind up with 10,000 bacteria in the system. Data will not always represent an exponential increase in values. You can also have an exponential decrease. In this scenario that we're given here, we have the price, the average selling price of a 32-inch flat screen TV over time. We started in 2005, then the next value is at 2008, 2012, 2018. If you plug these numbers in as they are to your TI-84, it'll overflow the calculator. It won't work. The problem is using numbers like 2005 are just too big for the memory on the calculator, okay? Or actually just gets in the process that they have, whatever the algorithm is for coming up with the exponential function. The algorithm cannot handle numbers of that size. So what do? You rescale. Rescale means to up with is something similar to this. If you did this in Excel, it may give you 924.014 times e to some number. I don't know what that number would be, t. You can take and plug in e to whatever that number is, and it'll give you whatever this base is up here. So you can readily convert from e back to the form a times bx by just taking e raised to whatever that initial number is in the exponent. That'll give you the base that you want to work with. In this case, we can tell that what we're working with is a model that is in decline or decay. The way that you can tell it's in decline or decay is our factor, the 0.892, is between 0 and 1. If this factor is between 0 and 1, you have decay going on. If you have something like this, we have a decay factor, okay, you can compute the rate of decay as 1 minus b, which is going to give you 1 minus 0.892, which will give you 10 or 0.108. And essentially it's saying that you're experiencing a 10.8% decline, or about 10%. Let's see if I can slide the 8 in there. There we go. So what this is telling us is that each year the price of the TV is going down by about 10%. Okay, part D asks what is the annual decay rate? Well, we already did that. It says 10.8%. Now, this last question here, 10E, is kind of an intriguing one. It asks you, does the graph have a horizontal asymptote? Well, what this really is asking is, as the values for t, look in the upper right corner here, as the values for t get really big, does the graph level out? And the answer is yes, it will. It does develop an asymptote, and whatever that value is that it settles in at is going to reflect what the minimum price of a 32-inch flat screen TV is going to be over time. So these asymptotes can actually represent something about the product's price behavior. They can represent all types of things, like ultimately where's a population going to settle in. You know, it varies with the problem. But the asymptotes are important. They provide you with good information about the system. There are two last ideas I want to make sure that click for you. One of them is doubling time. Doubling time is, as the name implies, the amount of time it takes for something to double in value. Let's take a look at an example where you invest $1,500 at 4.5%, and it is compounded continuously. By compounding continuously, that means we're going to use P of t equals P0 e to the RT. To work this out, into our P0 e to the RT, we're going to plug the 1,500 in for our initial value. We're going to take the where'd this go? We're going to take the 4.5%. We're going to convert it back to a decimal and plug that in for the rate, and that'll give us here an initial equation that we can use as our model for growth over time. Now, when you're asked to do the doubling time, that means how long is it going to take for whatever amount you started with to double. So what you can do is you can say, well gosh, we're starting with 1,500. Double that is 3,000. So what we're going to want to do here then is to take and set 3,000, okay, I'm working on this line right here, equal to our equation. You can start off by dividing both sides by this 1,500, and 3,000 divided by the 1,500 will give you 2. Then what we're going to do is we're going to apply the natural log to each side. Natural log and e cancel. So those two will cancel. But on the left side, those don't cancel. dividing by the 0.045, this gives us a value of 15.4 years for this particular account to double in value. So right around 15 and a half years to double in value. You can also solve this same problem graphically by graphing the model that you have. Okay, just take your equation, whatever it is, graph it, and then also graph what's the value we're headed to, the 3,000. You can look at where they intersect, bring it on down, and get an estimate there. Okay. Solving algebraically, solving graphically are both things that you will be asked to do come time for quizzes and tests. Half-life. Half-life, as the name implies, is the amount of time it takes for half the stuff to go away. There are situations where you have decay. Radioactive isotopes are one example. If you go into a hospital, have some imaging work done, they use different types of dyes and stains to help make the image clearer. One of the things that they use is radioactive material. They'll have you drink something, a big cup of whatever it is, and they'll have radioactive material in it. And hopefully that radioactive material isn't going to stay in your bloodstream too long. Oftentimes what they use for these dyes is a radioactive material that has a fairly short half-life. So for example, if they give you 10 milligrams of it, by the end of the week it might be down to 5, the next week down to 2.5, the next week down to 1.25, and you get the idea, it dissipates rather quickly. Another example where half-life comes into play in a medical situation is where you're looking at something like antibiotics. Let's say a patient is given 100 milligrams of an antibiotic at 8 a.m. and the drug is filtered out at a rate of 8.7% an hour. So that means at 9 a.m., 8.7% of the 100 milligrams will have been filtered out by the liver, the kidneys, things like that. And the question is, how long will it take for the bloodstream to have a total of 50 milligrams of the drug? This would be a time very likely where it would be time to administer another dose. So this half-life stuff comes into determining how often do you need to give a dose of a medicine. Okay, so let's start out with our equation. We know that for half-life we want half of whatever it was we started with. We started with 100. We want to end up with 50. So there's our 100, there's our 50. The rate, not the factor. Okay, the factor would be something like A times 0.9. This would be a factor. The rate is, see it up here in the exponent. Okay, so there is our rate. Notice it's been converted from a percentage back to a decimal. And what we're going to wind up doing is solving this equation in a similar fashion to what we did with the previous one. The first thing we're going to do is divide both sides by 100. 50 divided by 100 is a half. 100 divided by 100 is 1. Okay, so what that does is it allows us to take a first step in solving for t. Okay, here's that equation from the previous page. I'm going to apply the natural log to both sides, and the natural log and e cancel out, leaving just the negative 0.87 t on the right-hand side. You can do the natural log of 0.5 or 1/2, whichever you want to call it. You can do this natural log on your calculator, and it's a negative 0.693. Yes, there is a mathematical reason why this is the negative of the natural log of 2, but that's not something we're going to work with in this particular class. At this point now you have an equation. You're going to divide by this 0.087, and you divide both sides by the negative 0.087, and you get t is 7.966. Now you got to be careful here to remember what the units on t are. In this case it's hours. So what it's basically saying is that in about 8 rounding it off to 8. The reason is different people metabolize drugs, antibiotics at different rates. So this is just an estimate. And it's basically saying you'll have half of the stuff left in 8 hours. As with the previous one, we could graph our regression equation, graph the value that represents half of what we started with, look for an intersection point, and read that off, and that's going to be pretty close to 8 as well. This graph was created in Wolfram Alpha. Okay, you can do this on Wolfram Alpha, you can do it in Excel, whatever. On your calculator, just make sure that on a quiz or test you sketch a picture of the graph that you obtained, labeling it, see how it has the 5, the 10, the 15, okay, and then pointing out where you took the reading on the graph, just like I did here. Okay, so this would be x equals 8. That would be part of the answer on the quiz as well. Just a quick reminder, there is a difference between a growth factor and a growth rate. The rate is the percent of increase. The factor is, remember the 599.06 times the 1.188 to the x. The factor is the base. Okay? The growth factor is the base. And the growth factor is accomplished by taking 1 plus whatever the rate is. So that would say this is going to be 1 plus 0.188. This would be the growth rate. If you have decay, you can determine that by once again looking at this factor. If this factor is between 0 and 1, you have decay. If it's greater than 1, you have growth. The relationship between the decay and between the decay rate and the decay factor is as follows. The factor is 1 minus the decay rate. And remember, the factor would be something like 247.035 times 0.791. This would be the growth or the decay factor. The 0.21, which comes from 1 minus the 0.79, will give us the decay rate. This decay rate can be converted to a percent, in this case 21%. Okay, make sure that you take a look at the homework for section 3.7. There's a lot going on in this section, which is why I broke it up into 2 separate movies. Okay, I do not want you to go into this quiz and get shot out of the saddle. This stuff is involved. It's going to take some thinking. You've got to develop techniques for using some type of a device for solving and doing regression analysis. There's a whole lot going on here. Make sure that you put the time into this to be successful. Remember, as with all other homeworks, if they are completed after the deadline, whatever is finished after the deadline will have a 50% reduction in that part of the score. You will still keep the 100% of the score value for anything that is done by the deadline. Anything done after the deadline is fine. Okay? That's that much more that you would not have had otherwise, and that much more practice and skill that you will develop. But realize anything that's done after the deadline is done at a rate of 50% of the value that it would have had it been done before the deadline. Hey, I hope things are going really well for you with all of your classes. I look